Brian Finn. F-I-N-N-S. Well, thank you for coming back. This is part 2. First one, we went over the first 3 of his papers published in 1905. And today we're going to look at the last 2 papers, which are probably his most famous. Those are the ones on special relativity. So these were published first in July and then a second one in September of 1905. These 2 papers are probably his most famous. This is where it sets out what is now known as his theory of relativity. Einstein, turns out, did not like that name. He preferred to call it his theory of invariance. Namely, it was a theory about things that don't change rather than those that do. Special relativity was added later to distinguish it from his second major theory, which was his so-called general theory of relativity. That one we're not going to be talking about. I may mention it, but we're not going to talk much about it. The first theory of relativity goes all the way back to Galileo. Galileo, in one of his major books, which was called The Dialogue Concerning Two Chief World Systems, where he lays out the fact that the Earth goes around the sun, not the other way around. This is the one that got him into all the trouble with the Catholic Church. But he was trying to argue that all motion is relative. And in that book comes what is known as his parable of the ship. So I'm going to read a short excerpt from his book. This is Galileo. Shut yourself up with some friend in the main cabin below decks on some large ship, and have with you there some flies, butterflies, and other small flying animals. Have a large bowl of water with some fish in it. Hang up a bottle that empties drop by drop into a wide vessel beneath it. With the ship standing still, observe carefully how the little animals fly with equal speed in all directions about the cabin. The fish swim indifferently in all directions. The drops fall into the vessel beneath. And in throwing something to your friend, you need throw it no more strongly in one direction than another, the distances being equal. Jumping with your feet together, you pass equally in spaces in all directions. When you have observed all these things carefully, though doubtlessly when the ship is standing still, everything must happen this way, have the ship proceed with equal speed you like, so long as the motion is uniform and not fluctuating this way and that. You will observe that not the least change in all the effects named, nor could you tell from any of them whether the ship was moving or standing still. That's the essence of relativity. You can't tell if you're moving. He wants you below decks, you can't see anything, but from any measurement you make underneath, you can't tell whether or not you're moving. All motion is relative. This is basically one of the things that Einstein's going to take very seriously. He's going to take Galileo's idea of relativity to the next degree. To me, what probably motivated Albert Einstein was a question he raised when he was a young child, probably in high school, around the age of 16. He actually wondered what would happen if you could ride on a beam of light. Put your hand in front of your face. Would you be able to see it? How can you see your hand? Well, light from outside reflects off your hand and hits your eye. But your hand is moving at the speed of light. Would the light be able to catch up to it, reflect off, and could you see it? Would your hand be invisible? Wait a minute. Would you be invisible if you were riding on a beam of light? Now, the interesting thing is, at that point, it would be a technical challenge, but not a physical impossibility to accelerate all the way up to the speed of light. Classical mechanics does not say you can't do that. So in principle, yes, you could move alongside a beam of light. Now, when Einstein got into college, he realized, wait a minute, there's a problem here. Because our prevailing theory of light is Maxwell's equations. Maxwell says that light consists of, as I've shown here, an alternating electric and magnetic field. The oscillating electric field creates an oscillating magnetic field, which creates an oscillating electric field, which creates an oscillating magnetic field. And it's these two fields that mutually reinforce each other that propagate through space at a predesignated speed. If you're sitting on top of a crest of that light, the field underneath your feet is static. Static fields do not create magnetic fields. Static magnetic fields do not create electric fields. How could there be any light? The light couldn't exist. It would evaporate. But light does exist. What he has uncovered is a logical contradiction between classical mechanics and Maxwell's equations. That's what he's going to try to resolve. To me, that's how he should have opened up his famous paper where he sets forth special relativity. He does not. I'm going to read you how he actually began it. And this is, to me, really disappointing. He's correct. He's correct. And it's a much more technically sophisticated argument, not the kind of a question a child would raise, but to me, that's the question that has to be answered. So this is the opening paragraph. This is his paper. It's called On the Electrodynamics of Moving Bodies. And he says, take, for example, the reciprocal electrodynamic action of a magnet and a conductor. A magnet, a conductor. The observable phenomenon here depends only on the relative motion of the conductor and the magnet, whereas the customary view draws a sharp distinction between the two cases in which either one or the other of these bodies is in motion. For if the magnet is in motion, the conductor is at rest, there arises in the neighborhood of the magnet an electric field with a certain definite energy, producing a current at the places where the parts of the conductor are situated. But if the magnet is stationary and the conductor is in motion, no electric field arises in the neighborhood of the magnet. In the conductor, however, we find an electromotive force, which itself there is no corresponding energy, but which gives rise, assuming the equality of relative motion in the two cases discussed, the electric current of the same path and intensity as those produced by electric forces in the former case. Okay, that's great. What he's pointing out is that this is how we generate electricity. We have a coil of wire, we have a magnet. We move the magnet near the coil of wire, we generate a current in the wire. We can also leave the magnet stationary and move the coil of wire. We generate the same electricity. And what he's saying is there's two different explanations depending on which is in motion. Shouldn't there only be one because it's the same thing that's happening? And there are two different explanations. Personally, I like this contradiction better. And that's the one we're going to deal with, that's the one we're going to resolve, because he has to answer this. In this paper, he does something that mimics Euclid. Remember Euclid from high school geometry? What Euclid did was he set out 5 postulates. From those 5 postulates, he derives all of geometry. Isaac Newton and Albert Einstein were both fascinated by that idea. You set forth a couple of postulates, then you derive a bunch of theorems from that. This is how Isaac Newton wrote his famous book, where he laid out his classical theories of mechanics. And Einstein does basically the same thing, only he sets out with 2 postulates. The first one is what he calls the principle of relativity. This is his words. The same laws of electrodynamics and optics will be valid for all frames of reference for which the equations of mechanics hold true. Now, the equations of mechanics, that's what Galileo was talking about. Dropping objects, throwing objects, jumping, things flying through the air. Those are all mechanical. That's the parable of the ship. He's going to say, same has to be true for electricity, magnetism, and light. So he's just taking Galileo and simply saying, we're going to add on things that weren't known at his time and say, they also have to be hold true. His second postulate is the speed of light has to be a constant. It always goes with a definite velocity, which is independent of the state of motion of the emitting body. The speed of light is defined to be a constant. This is, in fact, what was discovered, if you remember last time, I mentioned the Michelson-Morley experiment where they were looking for the luminiferous ether and couldn't find it. The speed of light was the same no matter what direction the Earth was moving through the ether. Speed of light was the same. So Einstein's going to say, well, if Mother Nature is going to tell us the speed of light is the same, let's just take Mother Nature at her word. The speed of light is a constant, period. Those are the two postulates he's going to start out with. He's just going to take those and derive what are the consequences of those two postulates. That's the special theory of relativity. Here are some of the consequences. The first is the idea of simultaneity depends on your point of view. One person can say, those two things happen simultaneously. Another person will say, I watched the same two events and they didn't happen simultaneously. He's going to say, both people are correct. You can't say whether or not two things happened at the same time. It depends on your point of view or your state of motion. He's also going to discover the rate at which a clock ticks depends on how fast the clock is moving. And that clock is not just your watch, it's also your body, because your body basically is a clock. It has a metabolic rate. How rapidly you age will depend on how fast you're moving. Faster you move, the slower you age. It's also going to say that objects, as they move, don't have a fixed length, so that this object doesn't have an inherent length to it, depends on how fast it's moving past you. The faster it moves past you, it'll appear to shrink and become shorter in length. And finally, he's going to discover that the speed of light is in fact a cosmic speed limit. That's going to be what's going to resolve his problem with, can I ride on a beam of light? So, we'll take them one at a time. And I'm going to describe these not mathematically, which is what Einstein did, was he derived equations to go along with this. I'm going to show you instead a thought experiment that demonstrates the same thing. So this is not Einstein. Einstein did not do this in his paper. He did it with equations. What I'm going to say we're going to have was you have to go really fast. Einstein, oddly enough, the fastest thing in his day were locomotives. So if he had a thought experiment, it was let's consider a fast-moving train. Well, trains don't go quite fast enough. So we're going to use spaceships and say spaceships can go as fast as we want them to. We've got 3 spaceships. I'm going to designate the middle one to be the flagship. At the bottom, I set POV, stands for point of view. Our point of view for watching these events will be the blue ship in the middle, the flagship. And what we're going to have is we're going to have the flagship send out a radio signal. Now, radio signals travel at the speed of light. That is merely longer wavelength light that we can't see with our eyes, but it is electromagnetic waves just like visible light is. He's going to send out a radio transmission to the 2 other ships, the one in front of him and the one behind him. And the signal is going to be simple. Eat lunch now. And there's the signal going out, equally in all directions at the same speed forward as backwards, and not surprisingly, whoops, didn't mean to do that. Go back a slide there, didn't mean to do that. Didn't mean to do that either. Skipped ahead there. There we are, the 2 ships receive the signal simultaneously, as far as the blue ship in the middle is concerned. Nothing surprising there. Now what we're going to do is watch the same event, the transmission being sent and being received, but now we're simply going to watch from a different point of view. We now have a space station down here, and our point of view is the observer on the space station. He's going to see the 3 ships moving past him at high speed. He's going to see the blue ship send out the signal, and now the signal is going to go out, but notice the green ship is moving towards the signal. The distance that signal has to travel is going to be shorter. Therefore, that ship is going to receive the signal first. The red ship receives the signal second. As far as he is concerned, those 2 events, the same 2 events the blue ship saw, are no longer simultaneous. They are now sequential. Green happens first, red happens second. As far as blue is concerned, they happened at the same time. What is simultaneous from one point of view is not simultaneous from another point of view. Okay? Now, classically, that would not happen. Because classically, light would not move at the same speed in both directions. It would move faster going forward, slower going backwards, because its state of motion of the emitter, the blue ship, would in fact affect the speed. The signal going backwards would be traveling slower, covering a shorter distance, and the one going forward would be moving faster, covering a longer distance, and the two events would still be simultaneous. To see that, since this is not the way it actually happens, we have to do something a little bit different. So what I'm going to do instead is show you something a little bit different. Rather than shooting out a light signal, we're going to shoot out a soccer ball. This is literally, a truck is going to be moving forward at 60 miles an hour and shoot a soccer ball backwards at 60 miles an hour. And relative to the ground, the soccer ball will be at rest. Because shot backwards, it will be moving slower relative to the ground. That's what the light would normally do. So here we are.
I have a feeling that we are very close to a perfect demonstration. We're going to see that ball drop.
With the forward and backward momentum matched as close as they're going to get it, the pressure's on Grant for a perfect release.
I don't know about you guys, but that looked pretty good to me. Let's check the high speed.
It really looked good to the naked eye, but the judge in this case is the high speed.
Oh my God, it's like a cartoon. It's just in the air, it stops and it just falls.
Look at that.
Fantastic.
I mean, look, it doesn't move at all. It's going straight down. Dude.
Woo! We did it! We did it! Yeah! Vector edition! Yeah!
Light should do the same thing. Namely, it should go slower in one direction, faster in the other, to allow the two events to be simultaneous. What's different here is Einstein's going to say, no, light doesn't do that. Light doesn't behave like that soccer ball does. It's different. Light moves at the same speed, moving forward and backwards, and that's what makes the two events no longer simultaneous. Notice those two events are not causally connected. Namely, the light being received by the red ship did not cause the light to be received by the green ship. The two events were unconnected. Everyone agreed that the signal was sent out before it was received. Just disagreed on when the two signals were received. In fact, Einstein is going to argue the order of events here is irrelevant, therefore, I don't care which one happened first or whether they were simultaneous, because they're not causally connected. And not only that, they cannot be causally connected. The only thing we're going to preserve are events that are causally connected. Like we always agree, the signal was sent before it was received. And what he's really saying is, those are the only things we need to preserve. Those are the only things that are preserved. Things we don't have to agree on, we aren't going to agree on. Now you might wonder, okay, I thought I was going to hear more fancy stuff than this. This is pretty stupid. Is this what Einstein was famous for? Wait a minute. How do we know when something happens? You look at a clock and you say, the clock hit 2 o'clock at the same instant something happened, so the thing happened at 2 o'clock. But if I can disagree on when the simultaneity between a clock and an event, we can disagree on when things happen. That's a little more important, because that's how we know when things happen. Not only that, turns out the rate at which clocks ticks, now this is some mathematics we're not going to go through, the rate at which a clock ticks will also depend on how fast it's moving. So for an example, again, this is not Einstein because he didn't have spaceships. We're going to have two spaceships, and one we're going to put Alice, she's going to have a clock. The other spaceship, we're going to have Bob, he's going to have a clock. And what Einstein notes is that these two people moving past each other at high speeds, Alice is going to say, my clock's perfectly fine. Look over at Bob and say, Bob, your clock, it's slow. Bob's going to look at his clock and say, no, nothing wrong with my clock. Alice, it's your clock that's ticking slow. It's because each one sees their own clock at rest with respect to them, So it'll tick normally, but they'll see the other clock moving fast with respect to them and tick slower. The rate at which the clock ticks depends on how it's moving relative to you. Bob's clock's not moving relative to him, so it's normal. Alice's clock is moving, it's slow. What Einstein's going to say, they're both correct. Time is relative. And the reason is it doesn't matter whose clock is ticking at what rate. That's not something we have to preserve. Therefore, it can be relative to your point of view. He also goes further in saying it's not just these particular clocks, it's any kind of clock, including biological clocks. You will age slower. We'll come back to that in a moment. First question is, okay, I never noticed that happen. You should guess if this is true and we're doing real science, I should be able to notice that. I never did. Well, there's the formula that he derived. Plug numbers in there, and you discover at the speed of sound, which is, for most people, really, really fast, the effect is really, really small. That's the ratio of how fast your stationary and a moving clock tick. If it's 1, they're clicking at the same rate. It's a little bit bigger than 1. So the moving clock is ticking a little bit slower. Go up at the speed of a spaceship in orbit. The effect is still really tiny. Move at 10% of the speed of light. Now it gets to be a little bit noticeable. It's 0.5%. At 50% of the speed of light, now it's noticeable. So you have to be moving very fast in order for this to be noticeable. Or, whoops, sorry, the hand keeps. Or you have to take an extremely precise clock into in this case, an airplane with you. These are two scientists, Joseph Hafele and Richard Keating. They basically said, okay, Einstein says this, but I've never noticed it. But they know how to build clocks. So they took an atomic clock that could measure time incredibly precisely. They synchronized it with a second clock they left on the ground, put the other clock in an airplane, flew the airplane around, and then measured the difference. And they measured a difference of 0.15 microseconds, exactly in agreement with the predictions of Einstein's theory of relativity. That in fact, if you measure time very precisely, even at these relatively low speeds, the difference is tiny, but it's measurable with an atomic clock. You can measure the difference. This was done in 1971, and they published their paper and showed that, yeah, actually, strange though it may be, it's true. The moving clock did tick slower than the stationary clock, but you need an atomic clock to observe it. This has subsequently been done when you accelerate subatomic particles to close to the speed of light. There are some that are radioactive and decay. That makes them like a clock. The rate at which they decay is like the ticking of a clock. If you speed them up, they tick slower and they live longer. And that's now well established. This has some interesting implications. So what we're going to do is see, how does this work? We're going to go on a trip to a nearby star. It's the L98-59. It's a red dwarf star that's in the constellation Volans, which is the flying fish. It's in the southern hemisphere, so we can't see it in the night sky here. You have to go below the equator to see it. But it's an interesting one because it has a bunch of planets orbiting around it, one of which is in what is called the habitable zone. What that means is a possibility of there being liquid water on the surface of that planet, and therefore the possibility of life. So we can say, let's go there and see what's going on. Star is about 35 light years away. We're going to get on a spaceship that goes very close to the speed of light. We're going to say that you're 75 years old when you leave. You have a grandchild that's going to stay at home. It's only 15 years old. Traveling at 99.98976% of the speed of light. I picked that number so that you only age 1 year. However, on the Earth, take 35 years for you to go out there at close to the speed of light and 35 years to come back. On Earth, 70 years pass by. Your grandchild has aged 70 years. They're now 85. You've only aged 1 year. You're only 76. You are now younger than your grandchild. The typical way this is done is the so-called twin paradox. You have two twins, one that stays at home, one that goes out on a trip like this and comes back, and you have two twins that aren't of the same age. Okay, that's fine. But being younger than your grandchild, how can that possibly be? Well, this is how you do it. Now, you might, if you've really been paying attention, say, wait, hold on. All motion is relative. Why can't your grandchild say, I was the one that went on the long trip. You stayed in a spaceship and stayed there stationary the whole time in the spaceship. The Earth went out, turned around, and came back, and the grandchild was the one that went at high speeds, because relative to you, the Earth went away at 99.9% of the speed of light. You saw the Earth zip away, turn around, and come back. Why did you only age 1 year? You were sitting at rest in the spaceship the whole time. The Earth was the thing that zipped around and came back. Why weren't clocks on the Earth the ones that were slower? This is the paradox. How do we know which clock was really moving if all motion is relative? The reason is, you sitting there in the spaceship may have been sitting there the whole time, but you had to go from rest to 99% of the speed of light, turn around, come back, slow down, back to rest. You had to undergo acceleration. When you're in your car and you hit the gas pedal, what happens? You get pushed back. You then do a quick 180 and you get thrown all over the place. You then hit the brakes and you can feel that again. You experience those changes in your state of motion. Your grandson or granddaughter staying at home did not feel those. They never experienced those accelerations. The situations are not symmetrical. You were the one that actually did experience time dilation, not your grandchildren sitting at home. So they aged, if you will, normally. You were the one that aged slowly. The situations are not symmetrical. So there is not a paradox here. Let's just make sure we understand how this time dilation factor works. Right? That's one of the consequences, that time moves slower for moving clocks. Second one I mentioned was that things get shorter. Go back to the same three spaceships. We're going to send a signal out. The signal is going to be a little bit different, only now the order is going to be, I want you to burn your engine for 1 second. So the signal is going to go out from the mothership here, go out to the other two. They're going to be received simultaneously, and then both ships will now accelerate at the same rate at the same time. All of them will move together. What'll happen? Absolutely nothing. They'll all be the same distance apart, just moving a little bit faster. Nothing exciting happens as far as the flagship there is concerned. And again, we're going to look at it from the point of view of this observer on a space station watching these zip by. And again, the signals are not going to be received simultaneously, only now the green ship's going to get the signal first. They're going to accelerate first. The red ship is going to get the signal last, and they're going to accelerate last. And that's what's going to happen. They're going to close in on each other. He receives the signal first, he catches up with blue. Red receives the signal last, and the others catch up with him. Guy on the space station is going to go, whoa, is there going to be an accident? Because if they're moving fast enough, there could be. Blue ship is going to say, no, there's no chance of an accident. They never got any closer to me. Again, is this a contradiction? Einstein's going to argue the distance between the end of the blue ship and the front of the green ship gets smaller. Is there any difference between that distance and the front of the green ship and the back of the green ship? If this distance right here gets shorter, why doesn't this distance right here also get shorter? And that's what happens. All the distances get shorter, not just the ones between the ships, but the lengths of the ships themselves also get shorter. So therefore, as the ships get closer to each other, they actually shrink in size. Now you might say, whoa, 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 whoa. Wouldn't the people in the ship notice that? From their point of view, nothing happened. The ship did not get shorter. It's from this guy's point of view that the ship got shorter. He also will see the occupants of the ship get thinner. So you get thinner, you don't get lighter, you don't get lighter, you get thinner as the ship around you gets thinner. So as a result, you're not going to be more cramped. Everything changes proportionally. Length of ships gets shorter. So this is what the two observers see. This is what the flagship sees, and this is what the space station sees. They are different, but they're not inconsistent. So there's no contradiction here. Now, next thing he does, and I'm going to put the equation in here. This is what he literally derived. He then asked, okay, if I apply a force to an object to make it speed up, what happens? How much energy do I need to make something go faster? And he derives this formula. It's towards the end of his paper. And then you graph the results. So the red line right here is this equation right here. The blue line right here is what Isaac Newton would say. That's the classical physics. So notice I want to go 20% of the speed of light. There's not much difference between classical physics and Einstein's relativistic physics. If I want to go 80% of the speed of light, according to Newton, I only need a little bit of energy. According to Einstein, I need a lot more. If I want to go 90% of the speed of light, notice I need an awful lot of energy. The closer I get to the speed of light, the more energy I need. And in fact, to reach the speed of light, I need an infinite amount of energy. I'm sorry, you can't fit an infinite amount of energy in your gas tank. You can only fit a finite amount of energy, which means you can't reach the speed of light. This now answers Einstein's question. What would happen if I could ride on a beam of light? Well, I'm sorry, in order to accomplish that, you need an infinite amount of energy. You can't. Therefore, it's impossible to reach the speed of light. You cannot ride on a beam of light. Sorry. So therefore, there was no contradiction. Maxwell's fine. It's basically the classical physics that allowed you to reach the speed of light. That's the thing that's wrong. Okay? Speed of light is a cosmic speed limit. You can get as close as you want, but you can never reach nor exceed the speed of light. In fact, at accelerators, both in the United States and in Europe and elsewhere, we have managed to accelerate subatomic particles up to 99.99999, I believe it's like 9 or 10 nines of this percent of the speed of light. But no matter how hard we work, we can never get them to go faster than the speed of light. Speed of light does appear to be a cosmic speed limit. This is what he published in his first paper in July. He then sat at home waiting, how is the physics community going to react to my paper? And he basically heard very little. He then went back and looked at this equation and said, wait a minute, did I forget something here? In fact, he begins his last paper of 1905 with the results of the previous investigation, his July paper, lead to a very interesting conclusion, which is here to be deduced. What interesting conclusion was that? Well, here's his equation written out a little bit differently. KE stands for kinetic energy. That's how much energy an object has by virtue of being in motion. He's got it as the difference between two numbers. He's got to calculate one thing and then subtract something else. The first term turns out to be the total energy an object has when it's moving, and then you have to subtract how much energy it has when it's not moving. Wait a minute. An object has energy when it's not moving. And notice, it's not because it's hot, because hot objects have energy. There's nothing about temperature in there. It's not because it's gasoline at rest and you can burn it, because there's no reference to any chemical composition of the object. It's just virtue of the fact that it has mass. And this seems to be rather interesting. So what he's going to do in the last paper is try to figure out, what does that mean? Now here, he does in fact come up with a thought experiment. I'm going to modify Einstein's thought experiment, but this is in fact what appears in his final September paper. He says, well, light, which is radiation, is in fact a form of energy. And in his thought experiment, he's going to require that energy must be conserved. That's one of the basic laws of nature, the conservation of energy. And according to his relativity principle, that remains the same. Everyone will agree that energy is conserved. He's going to consider two observers looking at the same event and ask, what do each one of them see? And then try to reconcile any differences and see if he can use the idea of mass being related to energy to reconcile any differences between them. So he does not use Bob and Alice, but modern physicists always use Bob and Alice whenever we have a thought experiment. So we'll call them Bob and Alice. We've got Alice in her spaceship. She has a radioactive atom in her hand. And she's going to be zipping along in her spaceship. Bob is stationary, sitting there, and he's going to see Alice zipping by with her radioactive element. From Alice's point of view, she's just sitting in her spaceship. The atom is at rest. It is Bob that's zipping around in the opposite direction. So Bob's the one in motion. She's at rest. Right? Now, it's a radioactive atom. It's going to emit some radiation, some energy. Bob sees the moving atom emit radiation. That means some energy came out. In order to conserve energy, it has to come from somewhere. He can argue, well, the atom was moving. The energy for the radiation must have come from the motion of the atom, because that's a form of energy. All that happens is one form of energy turned to another form of energy. No problem. But what about Alice? Atom's at rest. It emitted some energy. Where'd that energy come from? Must have come from the mass. The atom must now be a little bit lighter, because that's the only way she can explain where that energy came from. What Einstein is going to say is these two explanations must be the same thing. Energy and mass must be identical. One saw a change in energy, the other saw a change in mass. Now bear in mind, he does some math in here to again rederive E equals mc squared. But one saw it as a change in energy, the other saw it as a change in mass. This is his key idea. There's E equals mc squared in Einstein's own handwriting. Both of them must be right. Energy must be the same as mass. The energy gained by the light must be equivalent to the mass lost by the atom. He then argues there's nothing special about this thought experiment. This must be something that is true in general. Einstein's conclusion. This appears in his paper. From this equation, it follows directly. If a body releases the energy E in the form of radiation, its mass decreases by E divided by c squared. Since obviously, here it is inessential that the energy withdrawn from the body happens to turn into the energy of radiation rather than into some other form of energy, we are led to the more general conclusion. The mass of a body is a measure of its energy content. The energy changes by E, the mass must change in the same sense as E divided by c squared. That was his conclusion. Why the c squared? Well, a couple of ways to describe why we have c squared. One is to simply say, well, all we're doing is following the logical deductions from his two postulates. And when you do the logical deductions, c squared simply pops into the equation. It's as simple as that. It's a logical consequence of his two postulates. It's true if it's confirmed by experiment, and we'll see it was confirmed by experiment. Another way to look at it is c squared is a conversion factor between mass and energy, very much the way that there's a conversion factor between the metric system and the English system. There's 2.54 centimeters in an inch. There's about 2.2 pounds in a kilogram. It's just a conversion factor. Another way to look at it is, in fact, we foolish humans always thought there was a distinction between energy and mass. We thought they were two separate things. In fact, we had a conservation law for mass, which came out of chemists, that in a chemical reaction, the mass always stays the same. And then physicists came up with a conservation of energy in thermodynamics. And we thought those were two separate laws. Well, Mother Nature basically says, no, you foolish humans, they are not. Energy and mass have always been the same thing. For some reason, you drew a distinction between them that was never there at all. Energy and mass have always been two different types of the same thing. Now, this is Einstein in his own voice. You can notice he has a heavy German accent.
It followed from the special theory of relativity that mass and energy are but different manifestations of the same thing, a somewhat unfamiliar conception for the average mind. Furthermore, the equation E is equal mc squared, in which energy is put equal to mass multiplied with the square of the velocity of light, showed that very small amount of mass may be converted into a very large amount of energy, and vice versa. The mass and energy were in fact equivalent, according to the formula mentioned above. This was demonstrated by Cockcroft and Walton in 1932 experimentally.
Okay, so he mentioned an experiment. So we'll take a look briefly at this experiment. This was something that was done by two people in 1932. What they basically did was they were one of the first people to basically split an atom. What they did was they took a sample of lithium, they bombarded it with protons, split the lithium into two helium nuclei and some energy. Turns out the helium was lighter than the lithium and the proton combined, which means some mass was lost, some energy was gained. They measured how much energy, and it matched Einstein's E equals mc squared. The released energy was compensated by the lost in mass. So what we did was we converted some mass into energy. This was similar to the kind of work that was done by two other scientists, Lisa Meitner and Otto Hahn in Germany. They were one of the first to basically split the uranium atom. They bombarded uranium with neutrons and split the atom there. It led to the first atomic bomb. Interestingly enough, Lisa Meitner was a Jew. She fled Germany, went to Sweden. The British went to her and said, will you come to the United States with us and help build the Allies' atomic bomb? And she said, no, I don't think so. Otto Hahn stayed in Germany. He, as it turns out, was not a big fan of the Nazis, so he refused to have anything to do with the German atomic bomb program. That was run by Werner Heisenberg. So neither of them followed through to build the bomb. But they were the first to split the atom, split the uranium atom. These were the first to split an atom of any type, and that was lithium. So that was the experimental confirmation of Einstein's suggestion that you can turn energy into mass and mass into energy. Now, some concluding comments. First, we started out last week with his work on quantum mechanics. And in many respects, Einstein laid the foundation for what became the theory of quantum mechanics. He became very disenchanted with it as the theory of quantum mechanics started introducing all sorts of ideas of probability. He did not like introducing probability into quantum mechanics. He famously was said to have stated, God does not play dice with the universe. He probably never said those exact words. But I like the fact that his compatriot there, Niels Bohr, who was also one of the founders of quantum mechanics, and the two of them had arguments left and right about how to interpret quantum mechanics. told Einstein, stop telling God what to do. He thought quantum mechanics was either wrong or it was incomplete. Eventually, he had to realize, no, it's not wrong, but he always believed it was incomplete, largely because it was built on probability. And usually when we have probability, it's because we don't really know what's going on. So we say there's a 50% chance of it raining tomorrow. Why don't we know? Well, because we don't really know what's going on in the atmosphere with enough details to be able to say with certainty what's going to happen. Einstein believed that when you talk about the fundamental laws of nature, there really shouldn't be any uncertainty or probability in there. It should either happen or not. And he was always very uneasy about the introduction of probability. So he became disenchanted with the ideas of quantum mechanics. As I mentioned, this was called the special theory of relativity because his 1905 paper was limited to things moving at constant speed. And he thought, well, if all motion is relative, why do I have to have the speed always being constant? Why can't I allow the speed to change? Namely, why can't I allow things to accelerate and still apply my relativity principle to accelerating frames of reference? This became his general theory of relativity. It took him about 10 years to come up with that. In fact, if you look at pictures of Albert Einstein in 1905, he's a rather young man. Actually, his hair tends to be fairly well cut and trimmed. He's got a nice mustache, neatly trimmed. Look at his picture in 1915. He looks more like your typical image of him. His hair's no longer as well maintained, and it's all gray and frayed. And it's because he worked intensely on developing his general theory of relativity to the point of exhaustion. This is where he came up with the idea that gravity bends and warps space and time. This was, interesting enough, confirmed by Arthur Eddington in 1919 when he saw starlight getting bent as it passed by the sun during a solar eclipse. And this was a dramatic confirmation of his general theory of relativity. As I mentioned, he did not like the idea that it was called the relativity theory. That was a phrase that was coined by Max Planck, and he preferred to call it his theory of invariance, because what he was really trying to do is saying the only things we have to agree on are the things that are really important. And that's what scientists should be doing, is finding the important things that everyone must agree on, like that energy is conserved, but not the rate at which a clock ticks. That's not important. Therefore, we can disagree on that. How long an object is. You might think that's fundamental. It's a basic property of an object, its length. It's going to say, not really. We can disagree on that. That can be relative. But the conservation of energy, that's important. We have to agree on that. Now, if you want to find out more about this, a little plug on this. This is a short and very good book written by John Rigdon. He's a physics professor. He wrote it in 2005, which was the 100th anniversary of the 1905 papers. This book describes all the papers as well as some background and some subsequent work that Einstein did. So I would recommend that book if you're looking for something to find out more about what Einstein did in 1905. And that concludes what I had to say. Questions? Yes.
Your statement about spaceship, as it gets closer to the speed of light, has to put out basically infinite amounts of energy. In a different frame of reference, does that mean, could you say that the spaceship is increasing mass infinitely?
That actually turns out to be a slightly controversial statement. When I was in college, that's exactly what we learned, that as you move faster, you gain inertia.
Yeah.
Turns out people now tend not to like to describe that. And that's because if the object gains mass, does that mean, we talk about general relativity, it can gain enough mass to turn itself into a black hole? And the answer is no, that's not going to happen. Therefore, we probably shouldn't say it's gaining mass in the literal sense. It's gaining what we call inertia, which is a property classically we associate, in fact, we say it's the same thing as mass. We probably shouldn't be doing that anymore. It gains inertia, not mass. And inertia is the resistance to change in motion. And that's what becomes harder and harder for it to gain more speed as it gains inertia. But its mass is the quantity of matter, and the number of atoms stays the same. Yes? This comes from, as notice, the light has to be now in something. When Einstein talked about the speed of light, he was talking about the speed of light in a vacuum. As light interacts with matter, in effect, it slows down. That's why it has to be in a gas. If you create the gas correctly, in fact, this is why if you've ever watched light basically get refracted inside a glass of water, that's because the light moves a little bit slower in the water than it does in the air. And that's only a little bit slower. If you build a boson gas, you can actually make it slow down a lot, but it's because it's how the light is interacting with the particles, but not how light moves in a vacuum. And I will grant you, yes, that's real confusing. Yes?
Another question concerning the experiment where they first split uranium.
Mm-hmm.
Why didn't that lead to a chain reaction and an atomic bomb in their lab?
Because you have to have, because what happens there is you have one uranium atom, you hit it with a neutron, it knocks out two lighter atoms and a bunch of other neutrons. Those other neutrons have to then, because neutrons are unstable, they decay. Before they decay, they have to be able to hit another uranium atom. And if your uranium atoms are far enough apart, your uranium sample is not dense enough, they won't be able to do that. They'll either escape into the air or they'll decay. So you have to be able to compress the uranium together in order to create, in fact, I believe they use natural uranium, which is only like 0.25% of fissile. So in one sense, if you will, they probably were lucky.
Is there anything at the subatomic level that explains what goes on at this?
The subatomic level is where we usually see these effects. We don't usually see them on the large scale, because we usually can't get things anywhere near the speed of light. But when it's subatomic, we absolutely can get things close to the speed of light. So these effects are usually seen in particle accelerators. And that's usually where you have to worry about them. Yes?
In the diagram with the spaceships sending out the radio signal and receiving the Doppler shift type of
that you worry about the Doppler effect is if you're trying to measure the frequency of the light. Where you have to really worry about the Doppler effect, I mentioned the different ages of you and your grandchild. If you want to actually calculate, there's one way to measure to compare your clocks, okay, is you agree ahead of time. Every month, each of you is going to send a radio signal to the other one, okay? So that's how you can compare your clocks. You can see how often do I receive signals from my grandchild, how often do they receive signals from me. There you have to worry about the Doppler effect because the Doppler changes the time between the signals being sent because that's the Doppler effect, the frequency of the light. Here, what you would be frankly hearing is for the light going backwards, you'd be having a Doppler effect and he might hear something like this. Whereas the other might hear something like this. But they'd still hear the same, the message, they might be distorted by the Doppler effect because the frequency in the signal might be altered either high pitch or low pitch.
but if you get light
Yes, the faster you move, the bigger the Doppler effect is, yes. Yes, exactly correct. Yes.
Are you aware that in 1903, a scientist, Wellesley published a paper on E equals MC squared?
Yes, you mentioned that. I looked into that. That paper, my understanding was he did not derive it. He just noted that you take a mass and multiply it by a speed squared, you get an energy. And he suggested the speed you might use is the speed of light. But he didn't derive it from two postulates like Einstein did. And he didn't put it into a larger context like Einstein did. And therefore, it's Einstein that gets the credit for coming up with E equals mc squared, because he did derive it from fundamental postulates, put it in a larger context, and developed, in fact, he basically replaced all of classical mechanics with a new form of mechanics, special relativity. And of course, he then went on to generalize that and connect it to gravity. Yes?
Another question. As I understand, matter hasn't been really explained. Dark matter, and I don't know anything
Okay, now we're going beyond Einstein. But where dark matter comes from is basically using the Doppler effect. We notice that most galaxies are basically spinning, like our galaxy is spinning. And what we notice is that we can measure the rate at which they're spinning by looking at one end of the galaxy. We see them like moving towards us. And the other end, we see them moving away from us. So we see one blue shifted, one red shifted. We can measure how fast they're spinning. And then we notice how much mass there is by looking at the stars inside and estimating the mass of the galaxy. The galaxy is being held together by gravity. If the gravity only comes from the stars, it's spinning way too fast. The stars on the outside should be flung away. They aren't. Therefore, the guess is there has to be some matter holding the galaxy together. We can't see that. And because we can't see it, we call it dark. It exerts gravity, so we're going to call it matter. So therefore, we call it dark matter. What it is, we have no idea, because we haven't been able to detect it in a laboratory. There have been various attempts to try to create it in a laboratory, or in fact, if there is dark matter, bear in mind, we live on the outer edges of our galaxy. There should be dark matter in this room. So there have also been attempts to say, okay, if it's here, we should be able to find it. To date, nobody's found anything that can unambiguously be called dark matter. So therefore, we don't know what it is. We only know what it does. It holds galaxies together. Yes?
You mentioned this, I think, in your talk here. What is the constant between energy and mass? Multiply mass in pounds versus kilograms, what is it?
The difference is the speed of light. It's the conversion factor between mass and energy.
What is the constant?
3 times 10 to the 8th meters per second, then squared. You can express it in terms of kilograms per joule. And joule is a unit of energy. Questions? Yes. Yeah, that was one thing I did mention back here is why is C squared appeared in it? And one answer is that if you do the math, that's where it comes out. In fact, going back to here, this is the equation he derives at the end of his paper. And that's it right there.
Yeah, I agree it's the number, but it's not wrong.
It shows that light is not just like sound. It's got to be a lot more fundamental. And I've seen some people say that the speed of light is really the speed at which causality happens. So it's really basic and fundamental. It's not just the speed at which something happens to move through the air, like sound. Speed at which photons move, yes. It's not something, that's why it's amazing. It's not something you would have guessed. That's a philosophical question because they are both a wave and a particle. They have both properties. They interact like a particle, but they move like a wave. And that's a really weird thing. I will grant you that. In fact, unfortunately, it turns out that everything does that. Electrons do that, protons do that, atoms do that. It's just that some behave more like particles and a little bit like waves, and some behave more like waves and a little bit like particles.
Photons have mass because that little experiment with the black and
They have something that acts like mass because they have momentum. And usually we say something with momentum, that's mass times velocity. It's inertia in motion. That's a classical concept. And therefore, anything that has momentum has effectively mass. A French scientist by the name of Louis de Broglie wrote down an equation that connected momentum only with a wavelength. So anything with a wavelength has momentum. Light has a wavelength. Light has momentum. And one can also say, well, it's got energy, and energy and mass are kind of interchangeable, so can't we say sort of has mass? And in fact, as Einstein discovered in 1919, it's deflected by gravity. Well, what's deflected by gravity? Things with mass. So in a sense, yeah, it kind of does have mass. Yes?
That also why light.
Oh, and gravity, yes. Yes. Effects.
Because light has.
Got to be a little careful because, interestingly enough, Isaac Newton also predicted that light would be bent by gravity. But it turns out it's not just that, it's also the space itself is getting bent. And Einstein predicted that the space around the sun is, looks kind of like, oops, kind of like that. So therefore, it's not flat. So it's following the contours of space and gets bent. If you just say it's bent like mass, you only get half the deflection that we notice. Get the full deflection, you got to include that as well. Good questions. See, when I taught physics in high school, this is not on the MCAS, it's not on the AP exams. So therefore, when kids raise questions like this, I always had to go, we really have to cover the conservation of angular momentum because that's going to be on the test. This isn't. And it was always kind of frustrating because, yeah, these are really fascinating questions. And yes, we want to be able to talk about them, but they're not going to be in the MCAS exam. So, well, thank you very much.
Thank you.